In this example, we're going to use Newton's method to try to find an intersection between these two graphs, right? And so an intersection is typically a Newton's method finds us an x-intercept. So we're going to take these two equations and we're actually going to mix them together and we're going to figure out how we can turn it and use it into Newton's method. So original thing is that we are looking to see when cosine of x equals x. So Newton's method isn't going to work for that, but we can take this and manipulate it pretty easily just by bringing the x over and looking at cosine of x minus x equals 0. Because what Newton's method does is it finds x-intercepts. And so if I set it equal to 0, I'm now looking for x-intercepts. So perfect. So my original equation is cosine x minus x. And then I need my derivative. So that's going to be the derivative of cosine is negative sine x. Derivative of x is 1 with a subtraction sign in between them. All right, so don't forget Newton's method. The formula for Newton's method is our next iteration is based on previous x value minus the y value at that x value divided by the slope at that x value. All right, so we need somewhere to start. And so if I kind of think of the graph of cosine, it's tricky because this is 2 pi, which is 3.14. So this is pi, 3.14. So this graph on a cosine graph is looking like this. And then our linear equation is looking something like this. So that's 3.14. That's 1 point something, 1.57 because it's pi over 2. And so, I don't know, maybe this thing crosses somewhere over here. So we got to figure out some value. And so I'm going to start with just a nice number of a 1. I don't really know. And so I don't know if that 1 is here. I don't know the steepness. I'm just taking a guess. But I needed something to start. And I want it to be as efficient as possible. I don't want to do all these iterations. Even with a calculator, I don't want to do it. So I need somewhere to start. It's going to be somewhere, maybe a 1. I don't know. So to start this process is I'm going to be using the calculator. And so first thing I want to make sure that I have is things are in radians, right? And then I'm going to, into my original equation, I'm going to be doing cosine of x minus x. And then my second equation, I'm going to be doing my derivative, sine of x minus 1, right? I'm going to quit out of that. And then I'm going to start by storing. So 1 is going to be stored as x, right? And then I'm going to just build this formula. So I'm going to go x minus this fraction of, I'm going to do the y value. So y1 is my original function. I'm going to do y1 at x divided by y2, which is the slope equation at that x. And there's my Newton's method, which I already stored the 1 in, so it's actually going to run that. And so it's going to give me an x value. So I have a 0.750363867. All right, so I'm going to start kind of rolling through this and doing it over and over and over and over again. So hopefully I don't have to do too many iterations until this thing starts to repeat itself. So the second one is going to be storing this previous answer as x, and then go ahead and run a Newton's method again. So 0.7391128.909. I'm going to store it as x. So our third iteration, 0.739. So those are the exact same. So we're getting there. 0.8513334. We'll run it again. So store it as x. Run Newton's method again. So our fourth iteration is 0.73908.513. So all of that's locked. That's locked all the way out to here. So I can pretty much promise that that next one, if I store that as X and I run it one last time, nothing's going to change. So that's as accurate as we can get for those two crossing each other. And so what we were looking for is we were actually graphing, if we graphed this, we'd look for an x-intercept. But the original is trying to figure out where these two things cross. I had no idea I needed somewhere to start, so I took a rough look at what the graph might be and ran Newton's method a couple times, and I got the x-intercept, or I got where they cross each other.